Howdy 2021ers, this is Professor Kaufman, and what follows is an overview of Project 4. This project is focused on, as the title indicates, performance optimization and timing of code. It features two problems, one in which you'll be writing an optimized version of a provided function and attempting to earn points on a benchmark by achieving speed up over the provided version. And a second problem that reverses this, where we will provide a bunch of functions, and it will be your job to construct a benchmark for it. This time not to speed anything up, but instead to observe the inherent differences in timing and explain them in terms of cache and other forms of performance. Let's start with problem 1 over here. It is a matrix diagonal sums problem that bears just a little bit of discussion. If you have not encountered matrices before, then this will be a crash course in them. They're a fancy word for a 2D table of numbers and feature prominently in mathematics and engineering of all sorts. If you go on to study any form of machine learning or various graphics problems, you'll no doubt encounter matrices and vectors of one sort or another. Our intent and purpose here is just to calculate one specific mundane property of them. As you would have a 2D array of numbers like this, and typically this is the way that they're represented in C as 2D arrays, we'll calculate the sums of the diagonals for them. For instance, there's this diagonal that's colored sort of goldenrod here that marches down the elements 0, 0, 1, 1, 2, 2, 3, 3. This is a row index followed by a column index up top. Typically in a matrix parlance, this would be called the main diagonal. It's the one that's sort of in the middle. And all we really want to do is to calculate a total of the numbers that are in this diagonal. So it'd be 0 plus 6 plus 12 plus 18 plus 24. Add those up and you get 60. There are other diagonals in here, and this diagram is colored according to those different diagonals. For instance, below the main diagonal is this cyan colored one, totaling 56 down here. The green one, a little bit shorter, this salmon colored, and finally the pink one in the lower corner, which has just a single element. There are similarly some that are in the above the main diagonal, sometimes called the upper triangle of the matrix. And while there's no standard, completely standard numbering scheme for these, we'll adopt one that's slightly, unstandard, which is that this lower left diagonal, the pink one with the single element, that's diagonal 0, and then the one above it is diagonal 1, diagonal 2 is up here, that's in green, and so on and so forth. Later on in this project specification, there's actually a numbering scheme that allows you to say, oh, for this row number and this column number, which diagonal is it in? And that'll be a good thing for you to keep track of and study, as it'll probably pertain to the code that you eventually write. At any rate, I want to get myself an array of numbers, D0, D1, D2, D3, etc., that has these values in it, 20, 36, 48, 56, 60, 40, 24, 12, and 4. That's the sum of each of these diagonals working progressively from the lower left to the upper right. You notice the diagonals aren't necessarily the same length, that the main diagonal is the longest, and they get shorter as you go up and down in it. To that end, the sums are probably not going to be necessarily different. Primarily, we're doing this because the natural way of doing this, of going down diagonals visually like this, turns out to be not great for memory performance, but more on that later. All right, with that in mind, given this sort of matrixy thing calculates the vector of diagonal sums over here, we'll next move to some code that will actually do this for you. It's been in the code pack called SumDiag base normal over here. It features the sort of natural way to calculate these things, where you start with the 0th diagonal and work your way up. So this 0th one here, and then the 1th and the 2th, the 3rd. Interestingly, this will have a couple different loops in it, where this first set of loops iterates over those lower diagonals up to the main one, and then the second set of loops over here iterate over the upper diagonal. The numbering scheme is just a little bit different associated with those. And the code here is somewhat self-explanatory with the comments over here. At any rate, this version is not particularly fast, and it'll be your job to produce versions of it that run somewhat faster. And so this code that's provided then is measured in a benchmark. You'll be writing an alternative version of it, a function called sumDiagOptim. The first thing you might do in that respect is to copy over this version into your optimized version and just run it. We'll do that in just a moment, and then see what kinds of results you get. Basically, if you're running at the same speed as this thing, you're going to get 0 points. And part of your evaluation on this problem is to do better than this thing. Let's actually get that ball rolling right now. So I'm going to grab a link here to the code pack. Actually, I don't want to download it here. I instead want to copy it. And importantly, throughout this project, both on problem 1 and problem 2, since you'll be doing timing, we're going to have all students time their code on a specific set of machines. That's described over here, the evaluation on the login NN machines, where NN is 01, 02, 03, 04, etc. These are CSE Labs servers, and they're pretty beefy. Let me SSH over to one of them right now. Let's see, login 01.csclabs.umn.edu. Eventually, these are meant to replace the Atlas machines and possibly Apollo as well, because they're sizable and they do pretty well there. In just a moment, I should get a login here. No prompt for password because I had set up my SSH login earlier. I'll do, let's see, just let me make a directory. Actually, I think I have one. So Seaside 2020, good. Okay, I got some old stuff in here. I'll use a wget and paste that link I copied a moment ago here. So this will download that zip file directly to Atlas, and then I can look. There it is. Unzip that p4 code.zip. And that should inflate the code pack for today. So do whatever you need to do to get the initial code back where it is that you need to go to. And I'll come in here and, of course, fire up my favorite editor, Emacs, to start having a look at what's around here. Let's see. So this sumdiag, I guess I'll make this a little bit better. Sumdiag base, this is the provided code that's in there, and it should appear just as it does in the project spec. One thing you may want to do right out of the gate is to have a look at what these structs look like, this mat and this vec business over here. Those are defined in the matvec.h header file. And this is just a thin wrapper over some data that can comprise these functions, or this thing. So for instance, a vector is just a glorified array. We'll keep track of how long it is, so you can potentially do some bounds checking later on. And a matrix is sort of a two-dimensional array of numbers, but we'll talk in lecture, probably on Friday, about how all such 2D entities have to be mapped into one dimension. And so we'll facilitate that and potentially more efficient memory utilization of it by making use of just a one-dimensional array where those two-dimensional numbers are in, and then providing some getter and setter functions, for instance, these mset, mget, vget, vset functions over here. You can see those are used throughout here. For instance, to get a matrix element out, you provide the matrix itself or a pointer to it, the row and the column of the element you want to retrieve. And if you're curious about where all these functions are located, you can find those in the matvec util. For instance, if I search for mget over here, then you see, oh, this is just a little computation to say how many elements are in each row. Well, that's the number of columns that are in there. So if I say I want to skip the first 5 rows, the rows 0, 1, 2, 3, 4, that means I need to, and there are maybe 10 elements per row, so the column dimension is 10. Then the 5th row, not 0, 1, 2, 3, 4, skipping over those, the 5th row would start at element 50, because that's 10 elements times the 5th row. So start there and then go to some column entry, which would be 2 into that. So it'd be at element 52, that's where element 52 is stored. So these functions are sort of dead simple to understand. Potentially add bounds checking to it and stuff like that, but it's not much of a reason to do so here. So that'll be semi-important to recognize what those data structures look like so that you can employ them, but they're not complicated. They're just arrays, essentially. And calculating where any individual element of them is not too bad. Now our purpose here was to start filling in an optimized version of this. If you look in here, there is a sumdiagoptim.c file, but this has blanks in it. There's a suggested strategy here that you may want to try several versions of different optimizations, copy and paste galore, but the one that is ultimately called is this sumdiagoptim version over here, and in this case it's calling version 1. I can do a cheap thing here. For instance, come over to this base version. I'm just going to copy the entirety of this code, and I will paste it in over here. So my version 1 now is essentially the baseline version of this thing. I'm going to save that, and I should be in a position now, if I open up a shell, to do some compilation and actually run this thing. So make prob1. Let's see. I'll just type make. That should compile everything. So the freshly compiled sumdiag benchmark over here. Let's see. Where is that thing? Sumdiag benchmark. It's here. Okay, sumdiag benchmark. So if I run this thing, it's going to try my optimized version versus the baseline version on several different sizes of matrices. So, for instance, construct a 512 by 512 matrix, use the baseline version to sum up all the diagonals, and then call my optimized version to sum up the diagonals as well, and see if there's any speed up there. You can see this takes some time because, for instance, a 6001 by 6001 matrix, it takes 3 seconds for this baseline version to complete, 6 seconds for the 8192 size, and essentially I copied that, and so I'm getting no speed up whatsoever not associated with this, and I'm getting very few points thus far. So the gist of what I'll do next is to try and figure out things I might want to change about this code to try to make it run faster. There are some suggestions for that in the project specification. They appear somewhat lower down over here. I'll come back to the debugging things in here. This listing describes at a high level various optimizations that you may wish to try to employ to get things to go faster. For instance, we'll talk about this in the context of both code optimization and already talking about it in terms of the memory system. Repeatedly hitting main memory is less efficient than storing things in registers. And you'll notice over in this baseline version that's been provided, you're provided pointers to these functions mat and vec, and throughout repeatedly referencing fields of them, which is a dereference going out to main memory. This is probably not as efficient as it could be if instead we're storing those values in registers instead. And an easy way to get that, to encourage the compiler to do that instead, is to dereference these things. To, for instance, say, oh, instead of having a pointer to this thing, let me give myself an actual version of it. Maybe I'll call it mat1 and just dereference it over here. If I use mat1, for instance, mat1.rows, this is likely to be in a register versus mat arrow rows. You know at the assembly level is going to have to go dereference and go to some offset associated with this something. Typically, as you dereference a whole struct like this and store it, then the fields will be stored in some registers. Not necessarily all in the same register, as a packed case, as you have to pass an argument, but the compiler will probably put this in its own register, for instance, which will be faster than going out to main memory. Now, of course, mat1.rows here, mat1, I can't pass it into these functions over here because they take pointers. And that would actually be the next thing that's listed in the optimization barriers to eliminate. These function calls turn out to be fairly expensive. As we discussed in assembly, you're both jumping control from this function into a different one, which takes a little bit of time, but is not overly costly. Means you're hitting main memory by having to push and pop the return address in there. But more importantly, when you call a function, you'll follow the register calling conventions, and all of the caller save registers that were in use within this sumdiag version 1 up here, they're invalidated because you don't know exactly what this function is going to do. It could change RDI and RSI and RAX and RDX and RCX and so forth, which means for this function, the compiler has fewer registers to make use of. Now, if you look carefully over in the header file, there's also a macro version of each of those accessor functions and setter functions called mget and vget. Next week in lab, we'll discuss exactly what it is that macros do and how they're different from functions. But if you look at, for instance, the utility version of this, you can see for efficiency reasons, there's a bunch of use of macros over here. They're associated with an actual struct rather than a pointer to a struct. And so it might be a good idea to start optimizing by replacing some of those function calls with it. This is typically known as an optimization known as function inlining that we'll address and discuss somewhat more later in lecture. The remaining list over here, for instance, reordering memory so that there's sequential access and perhaps trying to hit the processor pipeline through optimizations like loop unrolling that we'll discuss later. These are also good things to try out eventually. At some point, hopefully, you instill enough efficiency in code that you start earning some points. You'd see that, for instance, in a run of this benchmark on login 01, in this case, by, for instance, seeing that the speed up here was not below 1, but instead was above 1. So I optimized and got this code to run 3 times as fast as the baseline version. There's a scoring scheme associated with bigger speedups lead to bigger points, and bigger speedups on bigger matrices lead to more points increase versus smaller ones are sort of easier to eke out better performance on. So the points totaled that are associated with each of the sizes of matrices you run on over here, they're listed over here, and the sum up then to a raw points, which is, I think, rounded, if I remember right, to be an integer value, capping out at 35. So if you get a little over 35, which is not hard to do, then we'll cap it at 35. Unless you significantly exceed 35, in which case there may be a little bit of makeup credit that is available to you. So that's motivation to work hard to try to get this optimized version to go as fast as possible. My suggestion to you is, as you come up with something that's pretty good, then copy it from a version 1 and copy it down to version 2, and then start making additional changes. And then in your sum diag optim, change the version 1 to version 2 down here to go reasonably fast. Now, in the event that your optimization sort of breaks the code so that you're not computing the correct results, you're liable to get a whole bunch of error messages. So for instance, over here, I just changed this over from version 1 to version 2. Version 2 doesn't do anything. So it's going to not compute the correct diagonal sums. And if I rebuild right now, let's see. Oh, I got, I'll just copy or comment out this version 1 because I made some breaking changes there. Recompile that thing. And then if I run it again, then I'll get a bunch of error messages indicating like, oh, the baseline version computed a diagonal sum in this 0th entry, for instance. And it does not match, your answer does not match that. In this case, it's all zeros. So to that end, you'll get no points for such submissions, because if you're optimizing, you have to maintain the correctness of code, still produce the correct results. So be aware and run the benchmark reasonably often so that you're aware of any breakage that happens there. Debugging those, particularly in optimized code, can be extremely difficult. And so one final thing is worth mentioning about this, that there is a printing version of this over here. So sumdiag print.c that's provided. It will call both the baseline and the optimized version, and then check and produce the complete array of results over here that allows you to determine where it is in your outputs things are going wrong, because it's hard to do for very large ones. So for instance, if I run sumdiag print of 5, this will do those two things on a 5x5 matrix. It'll show the matrix here so you can manually sort of check things out. So the sum of this diagonal here, 0, 6, 12, 18, 24, it's like it was in the diagram. I think that's number 4, so it should be 60. That's what's produced by the baseline, but my optimized version, because I'm doing nothing, produces a 0 over here. And it's marked with stars to indicate it's wrong. So this can help in debugging. You can run this on small-ish matrices of various sizes to see what's going on there. Part of the evaluation for this will be based on producing numerically better results, so that's 35 points. But in addition to that, there's some questions you'll need to answer about your optimizations. Those are in p4writeup.txt. It's a text file that's sort of in the style of labs and homeworks that contains some questions that you should just write your answers directly in. There's a copy of it in here someplace. Yeah, P4 writeup up here. And you'll want to fill in some basic sort of information up here. Copy your final version of that optimized version in. Copy that table that was produced in the terminal for the benchmark results in over here. Make sure to run on login 01 or up to login 06. And then this is the part that folks oftentimes struggle the most with, is describe at least 3 optimizations that you utilized in order to speed up code and why they're designed to speed up code. So this might be something like we were just suggesting, reducing main memory references, optimizing the pattern that you visit the matrix in for cache performance, things along those lines. Try to make sure that there are 3 distinct things. So students sometimes get confused and end up saying the same thing twice over, which will cause loss of credit. And you can see below this, there are also some write-up answers that you'll have to do for problem 2 as well. Okay, so that's probably enough of me blathering about problem 1. Let's move on to problem 2. In problem 1, you had a benchmark and were to write optimized code for it to try to improve and get results. You have sort of the opposite setup for this problem 2, wherein you have a bunch of functions. They are search functions. They're in this searchfuncs.c file. And it's your job instead to write a benchmark to evaluate these functions. So with that in mind, it's not a bad idea to start, once you understand the basics of what the search benchmark is supposed to do, to look at the provided benchmark, the sumdiag benchmark that's working on your matrix code. Look through this thing for inspiration about how to write a main routine that will time the code that's associated with these search benchmarks. So you can lift a whole bunch of things in here and plop them down in your own search benchmark. For the moment, though, let's talk about what this function or this code is supposed to do. So you have a series of data structures in here, arrays, linked lists, and trees. And the arrays come in 2 flavors, either a presumed unsorted array or a sorted array. And the idea behind this benchmark is just to examine whether to examine the various performance of classic linear search and binary search algorithms using appropriate data structures for them. So for instance, in an unsorted array, you can use linear search by looking at the 0th, 1th, 2th, 3rd element for the thing you're looking for. However, if the array is sorted, you should realize you can do a binary search to say, let me start in the middle. If the thing I'm looking for is less than the middle element, then I should go left. But if the thing I'm looking for is greater than the middle element, then I go to the right, and sort of repeatedly have the search space in that fashion. Linked lists generally are oriented in a way that it's easy to implement a linear search, but very difficult to do a binary search because they don't have random access. That instead, if you want a linked data structure to do binary search, then you do well to use a binary search tree. So these are the 4 data structures / algorithms that are to be used. The functions that are provided in the search funcs enable you to create an array of even numbers and a linked list of even numbers of arbitrary size and a tree of arbitrary size that's got all even elements. So for instance, if I made an even array of size 5, it would contain 0, 2, 4, 6, and 8. That's 5 total elements in it. The reason that only even numbers are present in there is to enable you to very quickly do a series of searches for things that are and are not in the data structure. And in a second, you do a search sequence of 0, 1, 2, 3, 4, 5, 6, 7, and 8, 9, 10, and find that half of those things in this evens array are present and all the odd numbers are not found. That's because for these 4 algorithms, they have somewhat different properties associated with searching for something that isn't in the data structure. For instance, searching linearly in an array for something that isn't in there will oftentimes lead you to have to look through the entire array, versus binary search in an array can much quicker sort out whether or not something is present or not. To that end, then, it's a good idea to acquaint yourself with all of the functions that are in that searchfuncs.c file. There's a bunch that do make evens for the various data structures. There's creation of those data structures and cleanup of them, some freeing style functions. And there are also search functions. Let's have a look just quickly at what's in there. Here's searchfuncs.c. So the basic search algorithms appear up top. A linear search and array, a linked list search and array. Both these are just a straight up for loop that iterates through the data structure. And if you find what you're looking for, return 1. If you cannot find what you're looking for, eventually pop out of the loop and return 0. Similarly, there's a binary search for the array and binary search for the tree. There are a few utilities for other things here that you don't need to worry about too much. But then there's some creation functions like make a tree full of even numbers, let's see, and free the list, free a binary search tree, etc. So if you just gain a quick mastery of what functions are in there, you will be able to make use of them to create your data structures, access them through searches, and clean them up at appropriate times in the benchmark. The purpose here is not to force you to write data structure stuff, it's just to use some functions and focus instead on the timing part of this. So there's some instructions given here about more or less what the flow of execution should be within that search benchmark. But I think the easiest way to understand this at a semi-high level is to have a look at some of the sample runs that are given here. Now, there's a semi-specific format expected for the output of this program, but it's not strictly adhered to. So for instance, in my version of this, I have a little uses message to remind me of how to use it. You're not obligated to necessarily put this thing in here, but it's never a bad idea. The executable itself, as you would run it on the command line, should take at least 3 parameters, and optionally a 4th, 5th, 6th, 7th, 8th, 9th version. The first 2 parameters pertain to how big of things are supposed to be evaluated on, just as in the SumDiag benchmark, where we evaluate on a size 512 by 512 matrix, and then a size 1101 by 1101 matrix. So to here, we're going to search in various sizes for things. For example, down here, with the parameters 1 and 5 leading off, the smallest size data structure we'll use, be it list or array or tree, is 2 to the 1th power. So the first size listed here is 2. The biggest size is 2 to the 5th power. That's 32. And that's why it's the last number down here. And then each step in the benchmark will double the size. So if I start at 2, then I'll double it to 4, and then double that to 8, and then double that to 16. And do my timings to see, as the sizes for this gets bigger, how does the performance change. The number of searches you do in a size 2 data structure then should be 4. And that's because the elements of that data structure will be 0 and 2. And so you search for 0, which is found, 1, which is not found, 2, which is found, and 3, which is not found. So double the size and have a little for loop that searches for I equals 0 up to, 2 times n or whatever. Half of those should be hits and half of those should be misses, as indicated over here. And in this case, the last parameter is LL. Forgive me for the font here. This is what a 1 looks like. This is what an L looks like over here. So, and that's short for linked list, as in all I want to benchmark in this case is the linked list. That's why this list column appears, but no other columns appear, for instance, for the linear search in the array, or the binary array search or the binary tree search. Just the linked list in this case. You can see here then some times are reported, as in it took 3 times 10 to the minus 6 seconds in order to do this search of searching within this size 2 list to do the search sequence, search for 0, then search for 1, then search for 2, then search for 3. The last sort of numeric parameter that's given here is the number of repeats. And so this search sequence, it can be done repeatedly. In this case, since I said 1, that's just once through this loop over here. You can see a similar thing in the SumDiag benchmark over here, that there's this list of sizes over here that you probably don't need an array of these. because in the search benchmark, it's going to be some size, then double that size, then double that size, etc. So no need for an array in that case. But instead, you'll note down here that there is a loop that, for instance, repeats over it. So having a similar sort of code over here where you start a clock and stop a clock and sort of time what's happening within this repeats loop is a good way to sort of set your benchmark up. In the sumdiags case, we have two functions to run, and they're always run, this baseline version and the optim version. However, you'll probably have some conditionals in here to say, if I'm supposed to do the linked list version, then I'll time that. If I'm supposed to do the linear array version, then I'll time that. But if I'm not doing that, then I can skip a portion of the code over here. And finally, the thing that you're actually timing here is to potentially do a whole search sequence. So there will probably be a loop in here, a search for 0, then 1, then 2, then 3, then 4, etc. So again, draw inspiration from provided code there. So with that, I want to caveat this whole thing by saying these are incredibly small times and will generally be inconsistent and untrustworthy. To that end, you should make use of this repeats parameter to scale those times up, as in don't do this search sequence 0, 1, 2, 3 just once. Do it again, a second time, a third time. In fact, do it 1,000 times. That should make these times about 1,000 times bigger, and you start to get better resolution at that stage and can actually trust it. There is a limit to the time resolution that most CPU clocks and measures of times within it can get. And I would not trust numbers that are below this threshold, 0.00001 seconds. And if they appear in any of your answers, then probably you'll lose credit for it. So make sure to use that repeats parameter to scale up. For instance, if we come down here and say, let's start at a size 2 to the 4th data structure, so that's 16. Stop at a size 2 to the 8th, that's 256. But this time do 10 searches. So the search sequence in this case is going to be on data structures that have 0, 2, 4, blah, 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 up to 30 in it. And the search sequence will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to 31. So that's 32 total searches in here. And if my repeats was 1, this would read 32. But instead, repeats is asked for as 10. That's this last parameter here. So actually 320 searches. These are still pretty small times, too small to trust. But I bet if I did not 100, but maybe 1,000, then this would start to go up 2 orders of magnitude. So be in the 1 times 10 to the minus 3 range. To be safe, I might want to move this up to 10,000 instead. And then I can actually maybe start to see times that I could trust between the binary search and array and a binary search and a tree. And that's notable here is like a BA, short for binary search and array, and BT, binary search and a tree. I'm comparing these two in this version at various sizes. Still, this is pretty small in terms of time, subject to some noise, so I'd expect randomly maybe the binary search is faster than the binary search and array. It's faster than binary search and the tree for these. But if I scale it up enough, I'll start to get more consistent results as this one's always faster or this one's always faster at this particular size. So hopefully that gives you some explanation then of some of these command line parameters are. Notably, some of you may never have had to write a program that has command line processing like this. Earlier in the class, you had to do it a little bit, but this will be great practice for you and enable you to convey information from the outside world into your program and therefore make your programs more flexible. You've been writing mains for quite a while that have always this prototype int argc carstar argv. That's because the calling convention for C programs is that main is going to receive a number, which is how many things appear on the command line, and then an array of character pointers that point at the strings that appear on that command line. So for instance, for this invocation of search benchmark 5, 10, 20, which is start at 2 to the 5th, go up to 2 to the 10th size, and do 20 repeats each time. argc will be 4. That's because 4 things appear on the command line. The 0th thing is always the name of the program being run. So that's always in argv. In this case, it will be search benchmark. The 5 appears at argv1, 10 at argv2, and 20 at argv3. But bear in mind, these are strings rather than numbers themselves. You want to make use of functions that convert strings into binary numbers. There's a mention of some of them. Let's see, somewhere around here. I think it's A to I. Yeah, several of these are useful. A to I, A to L, A to F. These are functions that convert string representations for numbers into either integer or floating point representations that can be added, subtracted, multiplied, etc. So that's useful to look up those functions if you're unacquainted with them. So they could be used, for instance, called on this 5 to convert it from the string 5, the ASCII character 5, to the 2's complement binary layout for 5. You can make your job a little bit easier if you always run the algorithms in a fixed order. So for instance, over here, there's a request, please run the linear array search and the binary tree search. And down here, please run the linear array search and the linked list search. It doesn't matter terribly what order you print these things in. And so if someone says LALL versus LLLA, produce the same output. It's just easier to have an if condition to say, if I'm doing the linear search in the array, run that first and then print the time associated with it. And then later I'll do the linear search thing. So you think of these, additional optional command line arguments, LALL, as little switches. Like, oh, I've got some extra stuff over here. Let me turn off all of the algorithms, and then I'll go through this one and any others that I share here. And if it happens to match LL or LA or BT, I'll turn on a particular one of those. And there's some description down here of how you might go about doing that. So generally, this program is not terribly hard to construct. It's not too bad by way of it, and it'll give you good practice at sort of timing things. Expect to use the clock function in there. But the meat of this is to answer questions about what you observe from it. So after you get things set up properly and are reasonably trusting of the timings that you're producing, then you'll want to start analyzing the questions that are described in that questions document. I'm going to jump to the web version of this. It's listed down here, but it's also in the code pack. So for instance, you're supposed to figure out what's the minimum size where you actually start to see some divergence of those algorithms. You should have hopefully studied linear searches versus binary searches and know that there is a big O difference that predicts theoretically what their time differences should be. However, big O stuff always says above a certain threshold, there will be some differences. Your job is to figure out what is that practical threshold. For instance, is it at a size 16 list, size 16 arrays? Is binary search versus linear search the same, or is binary search start to exceed it, or is the sort of linear search actually more efficient at that stage? It should be pretty small stuff, and expect to have to use a large number of repetitions, particularly because small size data structures, like they run almost instantaneously. We saw that up here, that if I use a small number of repetitions in these samples, like 1 or 10, I get untrustworthy times. So expect to have large quantities here, like 10,000, 100,000 or so, in order to get times you could trust for a size 16 or size 32 data structure. Aside from that, you're asked to do some specific comparisons between things. For instance, compare the two linear approaches. One uses an array versus one uses a list. And figure out, practically speaking, which is faster and why. Compare as well the binary searches in the tree versus the array, and try to figure out why. Particularly, the last question asks you to elaborate on your answers previously about what effects memory caches play in this. Where do they have an effect versus where don't they? And expect there to be some spots where they don't actually apply. And intriguingly, this can equalize what might intuitively seem like two different approaches, make them about equivalent speed. Okay, I think that's enough there. Oh, except to issue the following warning. Many students at 11:50 p.m. on the deadline are just getting their search benchmark program completed. And it usually takes an hour or two of careful thought and analysis to complete and provide good answers to any of these things. that oftentimes students will just do a quick run of stuff, write a sentence and paste it in here, and then lose a massive amount of credit on this. And if you check the grading criteria for this problem, you note that, yeah, there's some for the code inspection associated with the search benchmark and that it passes some test cases, but most of the credit is actually associated with your answers there. So make sure to give that adequate time to complete those, to think about them, to write about them, to talk to a TA about them if you're uncertain. Finally, there is a bit of makeup credit associated with this last problem, and it is to, once you have a search benchmark established, try to rewrite it in a fashion that's a little bit more expandable, that uses some interesting software engineering techniques, notably function pointers. And there's a tutorial on this that's linked over here. It is optional reading. I caution students, make sure to finish your search benchmark first, answer the questions associated with the write-up, and then consider working on this makeup credit instead. Generally, TAs and I will turn you away if you haven't finished your write-up yet, then we won't help you with the makeup credit. And starting with the makeup credit here is a bad idea. It's harder to do, and it won't produce any different analysis. Instead, it's a software engineering exercise to make the code prettier. So do some reading there if you care to, and start early if you want to make advantage or take advantage of that makeup credit. Okay, that's all I got for you. This is due in a couple weeks, and the week after Thanksgiving break ends. Have fun coding, and I'll see you all in class. Happy hacking.